Okay, guys, welcome back to CSC498. This is going to be lecture 11, which makes it the second last lecture in the course. And, this is a good time to reflect on what we learned. Well, we started off with very basic operational laws, saw some basic relationships between, performance like throughput, response time, utilization, demand, etc. But that wasn't really, satisfying. That wasn't satisfying analysis because we couldn't answer questions like, well, what's the probability? There's so many jobs in the system, maybe 3 jobs in the system. We couldn't get exact, representations or formula for things like the expected response time, etc. So, for the majority of the course, we imposed assumptions on these systems and we began to do more sophisticated analysis. And that when we did that sophisticated analysis, basically always by having an underlying Markov chain. But in order to analyze a Markov chain, rather I should say in order for a Markov chain to be present in our system, we had to impose certain assumptions. And those assumptions that we imposed were usually something to go along with the exponential distribution. We've been looking at systems that exponential distribution comes up everywhere. Whether it be an MM1Q, MMCQ, Jackson networks, any variation thereof, all the underlying distributions were exponentially distributed. And, that's nice. And we saw, maybe that might be a good assumption for arrivals, maybe not that great of an assumption for service times, for instance. But for the remainder of the course, for the remainder 2 lectures, we want to investigate these models that we've been looking at, take another look at the analysis and see, well, what happens, what can we accomplish if we start to relax some of these assumptions? Oh, one thing I forgot to mention, I'm getting like a weird glare on my camera right now, and when I say camera, it's just my laptop. But I think there's like hot light beams coming down. Maybe there isn't. Maybe it took care of itself. But I apologize for it. I need to get like a better camera if I want to do these things moving forward. I don't know. Maybe I can get the university to pay for it. We'll see. Okay, but I want to move forward and relax some of these assumptions and see if any form of analysis is still feasible, is still doable. Okay, well, the basic model that we were looking at was the MM1Q. Well, as I just mentioned and we talked about before, this first M is a reasonable assumption. That's saying jobs arrive to the system following a Poisson process. The inner arrival times to the system are exponentially distributed with rate lambda. Same thing. Okay, well, there's results that show in real life, or if you aggregate a bunch of arrival streams together, that's what it approaches. So you look at arrival streams where there's a high number of users, such as like data centers, server farms, etc. That's a pretty good assumption. What about this one? Well, this second M is saying the service times are Markovian. The service times are memoryless. Well, we haven't seen, any real-world data sets just yet, but I'll tell you right now, it's not the greatest assumption. It turns out that, service times really aren't memoryless. They really aren't exponentially distributed. So that second assumption there, maybe not the greatest. Well, for the next 2 lectures, we're basically going to see what we can do when we relax this assumption. So instead of it being Markovian, we put a G there, and you'll remember we talked about it briefly, but that G basically stands for general. So I'm going to allow the service times to be generally distributed. It's going to be able to be, uniformly distributed, deterministically distributed, Markovian distributed, other weird things like bounded normal, and we'll get into other distributions like Pareto and what we call heavy-tailed distributions, but we basically let it be completely abstract, completely general here. That's the first assumption that we're going to relax and see what we can do, what kind of analysis we can do and move forward there. And that's what we're going to focus on in this lecture. In next lecture, maybe a little bit at the end of this lecture, we're also going to begin to relax the service discipline. So you'll remember that it's basically encoded in the MM1Q, and it's suppressed there, but it should be inferred that in an MM1Q, jobs are processed following first in, first out. Well, what if we process them in some other way? And again, we might talk about it a little bit in this lecture, definitely next lecture, but I want you guys to begin thinking, okay, well, if we aren't processing things first in, first out, what might we do? What might be a better way to process things? So that's just a little thought experiment I want you guys to start to think about. But today, we're focusing in on this one. We're relaxing the assumption on the service time distribution. And of course, what that gives us is what we call the MG1Q. So you should be able to infer by now, okay, jobs still arrive following the Poisson process with rate lambda. Job processing times are going to be completely general, but we'll say the expected service time equals 1 over mu. So they can be distributed however they want. Might be deterministic, might be exponential, like I said, might be something else, but we know the mean. The mean is 1 over mu. So the rate at which jobs get processed is mu. And we have a single server. So before we get into the analysis of the system, maybe it's important to understand why it's difficult to analyze the system. Well, with an MM1Q, what do we do? Well, MM1Q, everything's exponential. We can just represent the state space, number of jobs in the system, and analyze it like a Markov chain. Well, let's see if we can do that here. Why can't we analyze it like a Markov chain? Why not? Well, let's draw it out. So I'm going to let the state space be the number of jobs in the system. It has an infinite buffer, just like an MM1Q, so the state space is infinite. You know, maybe we'll have things transitioning between these states, sure. And what do we label these arrows with? So this is the supposed Markov chain for the MG1Q. We'll see what we're going to run into some issues for now, but we're trying to build it up. Well, we know that jobs still arrive following a Poisson process with rate lambda. Okay, so, you know, we can put lambdas across the top. That's not actually the problem here. And to understand the problem, let's consider this case. We're in state 1. A job arrives to the system. So we're in state 1 and a job arrives. 2 questions. What state do I move to? And second, what's the rate out of that state that I just moved to? Okay, well, if you're thinking typical Markov chain stuff, well, what state do I move to? I'm in state 1, a job arrives, I'll move to state 2. Why not, right? So let's say I move to state 2. So I'm in state 2. Okay, what's the rate out? Well, you might say, well, jobs are being processed with rate mu, so it's just mu. But this is where perhaps the assumptions of the exponential distribution really come to light and why we're able to analyze these Markov chains, because we can't quite do that. Because we don't know how long we were processing the job in state 1. If we were processing the job for maybe 1 second here, and then a job arrives and we move to state 2, well, we'd expect the remaining processing time of that to be conditional on that 1 second, and that's going to affect the rate. For instance, the rate could drastically change if we were processing it for 1 second beforehand or a billion seconds beforehand, right? Just think of if job processing times were uniformly distributed, I get something like this, maybe it's between 0 and 1, right? And I look, okay, well, this has a processing rate of 0.5. Right? So maybe if I move to state 2, directly, or sorry, a mean of 0.5, it has a processing rate of 2. The mean is 0.5. So here, mu equals 2. And if, for instance, I've almost done no processing and I move to state 2, yes, I'm going to be processing the job here with rate mu, which equals 2. But let's say, for instance, a job arrives not when, basically I just started processing it, but maybe halfway through. Well, that's going to affect the rate. That's going to give me a new conditional remaining service time distribution. Well, if I know it's greater than 0.5, let's say a job arrives 0.5 seconds later. Well, I now know my conditional distribution for this uniformly distributed random variable now looks like this. And you think, okay, well, what's this remaining time? Well, you can think this is 0.75. So the remaining processing rate is going to be 1 over the difference here. I'll call this mu prime. This is going to equal 4. All that's saying is, okay, well, if I'm processing a little bit and then I move to the state, it's going to change the new processing rate because I have put in some processing time into it already. Well, why could we do this no problem before with the exponential distribution? Because it's memoryless. When we move to the state, it's like we started over the variable fresh, so we didn't have to worry about, keeping track of the previous processing time. And all those details could just get swept under the rug because it didn't matter because it was like a fresh service time anyway. Well, that's not the case here. So I can't just move to state 2 because I need to also keep track of the current processing time, because I don't know if I've come from state 2 from state 1, where I've been processing the job for 0.5 seconds already maybe, or maybe I'm coming from state 3 to state 2, where I just completed a job, so now I'm starting one fresh. So these mu's, the rates back here, I don't know what it is, and in fact it's going to be dependent. So you might say, okay, well, if we need to keep track of the service time, or the amount of work already put in to our job, how about we keep track of that in the state space? So instead of my state space equaling just the number of jobs in the system, maybe I let it equal something like this. It's going to be a 2-tuple number of jobs, and the second parameter is going to be, the amount of processing time I've already put into the current job being processed. So current process amount, we'll call it. Okay, well, instead of now there being like a state 1 like this, I still have, them being separated countably with the first parameter, but I have a group of states here now. And my marker is running out. Where did I put the other markers? Well, I think we'll have to cope with it for now. Hopefully we can make it through this section of the lecture, and then I'll find a new one for the next section. Okay, or next part, whatever you want to call it. So yeah, we might be able to transfer and whatnot, but you might say, okay, well, this is 2 jobs and it's fresh. We haven't processed anything. And you say, well, okay, you want to keep track of when there's 0.5 down here? Okay, well, we'll have a state where there's 2 jobs in the system and we've been processing the current job for 0.5 seconds. Well, maybe you need one for 1 second. And so on and so forth. But here's the problem. Number of jobs, that's countable. It's discrete. The current processing time, that's not discrete, that's continuous, right? The service time distribution can be at least a continuous random variable. And if it's a continuous random variable, I need a continuous state space for that. So I no longer have a countable state space. I have a continuous state space. So really these, states kind of flow together. And you'll remember one of the criteria for having a Markov chain was the state space becomes countable. So I no longer have a Markov chain, and I get like this gross continuous parameter for my state space in this other axis, you can think. Well, that's a problem, because that means there's really no way I can model this MG1 system as a Markov chain. At least I can't model it as a Markov chain in general. But there is something I can note. And when I say you can't model it as a Markov chain, essentially what I'm saying is this system is not memoryless. It's not memoryless because the amount of time I've, processed the current job matters. That's a piece of information I need to know in order to know, well, what's the rate to the next state. Well, in general, the system isn't memoryless. But can I inspect the system at any, specific points in time? And can I find these specific points in time so I know the rates for sure? Or in other words, these moments in time, in these moments of time, the system is in fact memoryless. Does there exist such points in time? Yeah, there does. And let's consider that. What if I look at the system as jobs depart, as jobs leave? If I look at the system at the points of time when jobs leave, can I determine the rates, the current processing rate and the current arrival rate, with just knowing the number of jobs in the system? Yeah, I can. Why is that the case? Well, imagine I have, take 5 jobs in the system, and a job leaves. Okay, so I had 5 jobs in the system, a job just left. Now there's 4 jobs in the system. I want to know, okay, what's the current processing rate and what's the current arrival rate? Well, the current processing rate, we know is what? We know it's mu. Why do we know it's mu? Because we are actually starting the job fresh. Because the 5th job just left. Now we're, taking the next one off the queue and we're immediately starting it. It's a fresh processing time. We know that there's 0 amount of time put into it. Therefore, the rate at which this job will complete is mu, because the expectation of the service time is 1 over mu. Okay, so we know departure rate equals mu. Of course, you need to be a little bit careful because, the departure rate's mu if there's more than, or there are jobs in the system. If there was 1 job in the system and then it leaves, well, that leaves no jobs in the system. But of course, we know if there's no jobs in the system, the departure rate is 0. Okay. What about the arrival rate? Do we know the arrival rate? Well, we just finished processing a job, but there's nothing saying that, it may have been 1 second since the last arrival, 5 seconds, 10 seconds, a millennia. We don't really know anything about since the last time the last arrival occurred. But here's the thing, remember, we're dealing with a MG1Q. The service times are general, but the arrival times are still Markovian. The inter-arrival times are still Markovian. We're still dealing with a Poisson process. Therefore, we know the arrival rate is lambda, because the arrival rate, the inter-arrival times, is exponentially distributed, and therefore it is memoryless. Okay. So if we inspect the system when jobs depart, the exact instance of time when jobs leave, we know the rates. And if we can analyze this in some way, look at the times when jobs leave and make some kind of analysis, we might be able to conclude something. We might be able to derive some system metrics, like the response time, the expected response time, expected number of jobs in the system. Well, this is what's called an embedded Markov chain. The system itself can't be modeled as a Markov chain, but there's moments in times where if we inspect the system at those moments of times, we can model it as a Markov chain. Okay, well, how is this going to help us? Well, I'm going to introduce some notation here. I'm going to say capital N, lowercase n. What's this going to denote? This is a random variable which denotes the number of jobs seen in the system as the nth job departs. When I say nth, I mean lowercase n. Seen in the system as the nth job departs. So imagine you're the 10th job to the system, or to arrive to the system. You get processed. As you get processed, you look behind you. Ah, there's 3 people left there. That would be N10. Okay. Well, here's the basic idea. We're going to try to build a recursion based off this. Then you let lowercase n approach infinity. And when you do that, you essentially end up dropping the subscript. And what we're going to be after is the expected number of jobs seen by departing jobs. Now we have to be careful here, because what are we ultimately after? Well, we want system metrics. We want the expected number of jobs in the system. And if we analyze it this way, what we're going to get is the expected number of jobs seen in the system as a job departs. Well, there's a selection bias there, and we need to deal with it somehow. But here's the nice thing. Remember, when we're dealing with a Poisson process, when jobs arrive, they see time averages. We get that pasta relationship, Poisson arrival, see time averages. So as jobs arrive, they see the system in steady state. Well, because of that, and what I'm thinking of doing, I'm not going to show you a proof of that here, but what I might do is it's just like a 5-10 minute proof. I might tag that on as an extra video, so I'm not going to show it in this section, but if you're interested, I'll post something to where we can talk about that proof. But because of that, we actually get this result that job departures also see time averages. Very important to note here, if I were to look at the departure stream, it's not necessarily a Poisson process, but they do see time averages. Okay. So if they do see time averages, I've addressed the selection bias. And again, it's not obvious that that's true, but I'll be posting a follow-up proof, depending on how long this runs, etc. Okay. So if I can solve for the expected value of this, I can then in get the expected value of the system, and from Little's law, expected number of jobs in the system, and from Little's law I can then get the expected response time of the system. So it seems like we're a little bit in business here. Okay. So remember, I said, what's the general strategy? Well, we want to build a recursion. So we want to get something like the expected, not the expected, but I want to be able to write out n plus 1 in terms of n. Well, let's try it. But before we try it, I'll hit you up with one more piece of notation. I know I always do this in my courses. It's always about notation. I'm going to say a at n. This is going to be a random variable, which denotes, a random variable, which denotes the number of arrivals which occurred during, the number of arrivals to the system during the nth job service time. So just again, imagine you're the 10th job in the system, you're getting processed, maybe it takes 3 seconds for you to get processed. During that time, maybe 2 jobs arrived. Then the value A10 would be 2. It's just the number of jobs that arrived to the system during the nth job's service time. And you gotta make sure our grammar checks out. It's possessive. Okay. Well, does that help me write out this recursion in any way? Maybe. Let's try it. So if I say the number of jobs seen in the system as, the n+1th job leaves, what does that equal? Let's think about this for a moment. I'm going to split it up into two cases. The first case, when n subscript n is greater than 0. What does that mean? Well, that means the number of jobs seen when the nth job leaves equals 0. Okay. And what's the other case? Of course, when it equals 0. Okay, so this is when the nth job leaves, it sees more than 0 jobs, so there's some jobs left in the system, and this one's when there's exactly 0 jobs left in the system. So when the nth job leaves here, it leaves behind an empty system. Let's zone in on that one. So you're the 10th job again. You're a 10th job to the system. The 9th job left, and it left behind an empty system. What does that mean when you arrive to the system? Well, that means you're going to arrive to an empty system. If the nth job leaves and it left behind an empty system, and you're the 10th job, so you're the job that comes directly after job 9, well, that means you're going to arrive to an empty system. Okay, so when you leave, how many jobs do you see? Well, I arrive to an empty system and I immediately start being processed. And when I finish being processed, I look behind, I'm leaving the system, maybe I see 2 jobs, maybe I see 3 jobs, maybe I see 10 jobs, maybe I see 0 jobs. But the number of jobs I see equals the number of jobs that arrived during my service time. Well, we have a random variable which denotes that. So that means, in this case, it's just going to be the number of jobs which arrived during my service time, during the n+1 service time. Oh, okay. Well, is the same true for this one? We have to be a little bit careful. Why do we have to be a little bit careful? Well, think about it. First of all, if this one's seeing 1 billion jobs, if the nth job leaves and sees 1 billion jobs, when you leave, you're going to see more than just the jobs that arrive there. So we're going to have to use the value nn in some way. So, okay, it's going to be the number of jobs which the nth job saw as it left. So we account for all those jobs. We're also going to have the jobs that arrived during our service time. So we get something like this. Is that it? Or do we need something else? Well, remember, when the nth job left, so maybe when the 9th job left, remember we're going to be the 10th job again here. When the 9th job left, it looked behind and it saw maybe 3 jobs. But in those 3 jobs, what's it including? It's including you. You're the 10th job. It's seeing some jobs left behind. You're in the mix. So when you leave the system as well, you have to account for yourself being counted in this value. So we have to make sure we give this a -1. Okay. Well, that's my recursion. Does that help me in any way? Well, I mean, it's a starting place. It's still far from obvious how this is going to be used. But let's see if we can write it in a slightly better way. And you may have seen this function in your math courses before, your stats courses, maybe your discrete math courses. There's something called the Heaviside step function. and you know, it's usually a cursive u at x, at some parameter x. And all this function is 1 if x is not equal to 0, and 0 if x equals 0. Okay. Let's think if that helps us in any way. And you know what? Before we continue on with the rest of the derivation, let's just pause here because we're probably, I'm not wearing my watch, we're probably coming up on a pretty long time, and these videos take forever to upload to YouTube. So take a look at this, see if you can write this using this without these cases here. So just like a single line of code using this Heaviside step function, and we'll continue the derivation in the next section. Thank you very much for your attention.